Good morning, everybody. Welcome back. My iced tea ready to go. Hope you guys are doing well. It's Monday, April 13th. We're getting ready to start up our 10 a.m. Class hour here for Chapman, Intro to Philosophy. Hope you guys are doing well. Good to see everybody this morning. Get comfortable. Get your viewing set up right. And we're going to just continue to talk a little bit about time, metaphysics of time, cap off our discussion of Einstein's theory of relativity, and then add a couple notes about Ted Sider. Hey, William, Kaylee, everybody else. Good to see you guys today. Hopefully you're doing well, staying safe and healthy. Always a pleasure to check in with all you guys. And finally, getting into that, hey Emily, getting to that point in the quarantine where I'm starting to play some extra video games and stuff. I don't know if you guys have any recommendations or anything, but I finally went out and got the Zelda game, Breath of the Wild, so starting to get into that. I downloaded the Goose game on Nintendo Switch. I don't know if you guys ever heard of that. It's kind of silly, but it's actually pretty fun. So, finally making a little time for the leisure. Not much else to do, so. Yeah, that and just, stuff to watch. Animal Crossing. Oh, yeah. I know everyone's playing Animal Crossing right now. I feel sometimes like I got to really think about, because I like a lot of these high action games and stuff, like I want to get the new Doom. But I like this Goose game. I like the Mario games and platformers and stuff. So, I could probably get into a little more family oriented. I know there's a lot of interactivity and the whole virtual world. So that might be next. But yeah, Goose game is a lot of fun. I'm still in the first part. I need to get the farmer to put on his hat, but I think I figured out that I gotta set up the picnic table first, or the blanket, and then, yeah, it's a fun game though. Anyways, yeah, playing my Nintendo Switch a little bit. Tetris 99 is a fun game, kind of competitive Tetris battle. Mario Kart. Yeah, I've been playing those Mario Kart Grand Prix and stuff. Hey, Brian. 150cc. I'm getting some gold medals and stuff, so soon hopefully I'll be able to unlock more playable characters and everything. Cool. Got about another minute and then we'll really get started. Any good movies recently? Let's see. What's the last one? I watched Invisible Man. I thought that was pretty good. I paid to have it on demand at home. Like over the last year, all the Best Picture nominees, a lot of them were really good. I liked Parasite. I thought Joker was really good. Not everybody was a huge fan, but I thought it was kind of like a masterpiece. I definitely thought that Joaquin Phoenix deserved Best Actor for sure. We've all watched the Tiger King, probably, documentary on Netflix. Decent. I don't know. How to Fix a Drug Scandal. It's another one, kind of true crime, and watching that. And I kind of ran out of steam for me though after like 3 or 4 episodes, just more of the same. But I've been watching this like Earth at Night on Netflix. Very cool. At first I thought it's just going to be another just nature footage, predators chasing after prey, but the night vision cameras and stuff is pretty awesome. Yeah, agree, Brian, for sure. All right, guys. Well, we're pretty much here. So it's 10 a.m. Thanks, everyone, for being back at our live stream. We're just continuing through our notes. We have more lectures this week on time. We started with that last class, and we are not done yet. So I want to say a few more things, give a summary of the Einstein, add a couple of extra little points, and then we'll try to talk about Ted Sider today. And that'll be our goal for today's meeting. As I've said before, all the previous assignments have been graded in the class, long time ago, the first essay, and a couple of weeks now, the midterm. So most everybody's checked on their scores, but anybody who hasn't, who still, obviously wants to know about it, simply send me an email, and I'll reply to your message with your score and any scanned images of the pages with comments too. So just letting you know. And then the next paper I'm not assigning yet. Per the schedule, it's not due until the 13th week. This is the 10th week. Usually I like to give about a 2-week window, and I might actually extend the due date slightly by a meeting or two, just to accommodate all the disruption to the schedule overall. But anyway, just letting you know, the prompt for Essay 2 is not to be distributed till next week. So we're just going through more lectures this week, and then we'll talk about the prompts and how to get a successful paper next week when the prompts are distributed to you guys. We'll talk about them here. Okay, so back to just a quick recap of Einstein. We're now on the subject of time in this class. What is the proper scientific and metaphysical understanding of time? And we were trying to just open that discussion by looking at some of the best current day theories of it, including the work of Albert Einstein, which is considered the standard in contemporary physics. So the theory of relativity, he starts by asking this question. Suppose there were two lightning strikes that occurred at separate points on a railway track. What would it mean if they happened simultaneously? Suppose they happened simultaneously, but what does this mean? Like, so this was the basic visual that he gave. So you got two lightning bolts. They occur at these two positions on the railway track. He says, suppose those two things happen simultaneously. Question, what does it mean to say that they happen simultaneously? He says, that's not so easy a question to answer as it might seem at first. You might just shrug your shoulders and be like, what, simultaneously, happening at the same time. But saying that they happen at the same time is not an informative description of what simultaneity means. It really just kind of repeats the definition in and of itself. We want to know in a more in-depth way, what does it mean for two events to happen at the same time? Einstein says, in fact, we need to have a robust definition of this concept, so much so that we could actually perform an experiment to test whether the two events were simultaneous or not. If we don't know how to test whether they're simultaneous or not, then he thinks this concept remains undefined and it shouldn't be used by a physicist or even an everyday person. So he says, what could be the test by means of which we could verify or disconfirm that the two seen lightning strikes are simultaneous? All right, well, he says, measure the distance between the length AB, where the two events occur, and take the midpoint and place an observer there, midpoint M. Here's the midpoint observer standing still motionless at the point M. Now, he said, if this individual standing still at M observes the two lightning strikes happening in the same visual perception, then relative to him, they would be considered to have happened simultaneously, as long as we make one additional assumption, that the speed of light is always constant and fixed, namely that the speed of light traveling from the path A to M is exactly the same velocity as the speed of light traveling from the path B to M. If the speed of light is constant and fixed, and if the two light sources arrive at this terminal point at the same moment to his visual system at the same point in time, then given the fact they've traveled two equal distances at the same velocity, we can infer that they departed from their origin points at the same time. And that, in other words, means that they departed simultaneously. So armed with the assumption that light always moves at a fixed speed, and given the fact this person is standing exactly equidistant from A and B, we could deduce from the receipt of the two light signals at once by him that they were derived from two departing light signals from the two positions at the same time. Now, after that, though, he said, it gets a lot weirder, though, when you consider another observer who's not this person, but who's passing through the scene with velocity v on a moving train. So say now we have the second observer here, and they're being carried to the right with constant velocity v, that they will traverse the midpoint M prime at the same moment that the motionless observer conducts their observation from point M. So the second observer carried to the right with velocity v, who for a split moment is parallel and perfectly aligned with this observer on M. He passes through M prime when this guy sees the two events happening simultaneously from his position. But since he's being carried away to the right and does not remain motionless at M prime, he's not going to see the two events happening simultaneously. He'll see them happening in a different order. So who can remind me, what is the first lightning strike that this person sees as he passes through M prime and continues traveling to the right with velocity v? He does not see them happening simultaneously, the guy on the train. Correct, William. He sees B happening first. And could you just give me like the quick breakdown of why is that? Why doesn't he see them happening at the same time? This guy did. Why doesn't he? what's the difference between the two that causes the secondary observer to see a different order of the events? What's the reason there? There is a reason, and it's something not too hard to state, I believe. So what is the reason that the second man moving toward the right, away from A and towards B? Okay, William, you say, and so does Brian, because he's closer to B when the light of the strikes reaches his eyes. Yes, the train is moving towards B. That's right. So for him to perceive these events, the light has to reach his eye. But light travels at a finite distance. It's not just magic how vision works. For example, if you close your eyelids now, you won't see things because the light rays incoming to the eye have been blocked by the eyelid. So for the light signal to reach his vision system, his eyes in other words, they have to be traveling toward him and they have to arrive to his body. But he's moving a farther distance away from A shorter distance closer to B. So two things moving at a common velocity cannot possibly catch this moving target at the same point, since he's moving further from one and closer to the other. This is the reason then that relative to the second observer, B is observed to happen first, and then after that, subsequently, the light source from A will catch up to him and he'd see it. So the first guy, the light sources travel an equal path distance because he's motionless, waiting for them there. But if that's what he sees while he stands at M, then while this second person passes through M prime as he conducts his observation, he's running away from the first light signal on the left and towards the second one. So he sees B first. And again, I think I mentioned that if you had a third observer on the scene who was moving in the opposite direction of travel, from right to left, then this third observer moving to the left through M double prime, he's going to have another result himself. And he's going to see A happening first, yet after that B. And for the exact same reason, parallel, just going in the opposite direction. So this generates a very, very weird and puzzling, even bizarre set of facts to consider. What we're being told is that the two events, lightning strike A and B, there's no objective fact as to what order they do occur in. According to one condition of observation, the motionless observer at M, they happen at the same time simultaneously. According to a second observer, the one who's in the path of motion headed to B, passing through M prime, B happens first and then A. And the third observer, traveling in the opposite direction, sees a third possible outcome, that it is A first and then B. So what is the right answer to the order of A and B? Are they simultaneous, or does A happen first, or does B happen first? The correct answer is that it's relative, and each of these different possibilities is entirely justified concerning the condition of the observer and their state of motion relative to the observed events. Now, don't misunderstand the point of this whole thing. It's not being claimed that they're really simultaneous and two other observers in motion see something that's other than reality. No, no. All three observers have equal claim to being the correct observer, because there is no point in space from which to observe things which is considered the objective observer's viewpoint. Since all objects are in motion relative to other objects considering some frame of reference, there's no privileged point of observation. So in fact, there's absolutely no objective fact about how these two events are to be organized in a sequence. Once you see that fact, that outcome of the theory, it gets very deep and very trippy, because what it means, among other things, is that there's no objective linear ordering to any events in the sequence of space-time. So what you consider to be in your own future now, an event that has not yet happened and is yet to be, could be seen as having happened already in the past, according to another possible observer positioned somewhere in space-time. So when you think, for example, that the past is gone and can't be altered, and that the future is wide open and anything can happen because those moments are yet to be, this, according to the space-time theory, would not be correct, because what events you consider to be in your future are only relatively so, considering your point of observation in space-time. Thus, we get to the very strange result that all events in space-time are equally real, inclusive of the past, present, and future. So in that way, all events are fully laid out, and you just experience them in a certain order for some strange reason, but your consciousness in that case is out of sync with the objective facts about how reality is organized and constituted, because it doesn't proceed in an unfolding linear fashion, but rather that's an illusion created by the conditions of your consciousness, and the actual fact is that in reality all the moments are equally real. Since we would have to account for them in this relativity of simultaneity thought experiment and physical experiments that have been conducted to show the same. Now I want to show you a couple of more strange elements having to do with this Einstein theory. And so the next thing I want to show, I'll just erase here, is the concept of time dilation. Time dilation can be understood by means of the case of a light clock. Okay, so imagine that what I'm showing you here are two planes of glass that are reflective, like mirrored surfaces. Take a photon of light and say that we excite this photon, sending it towards the top surface of this glass. Because it's reflective, it will bounce the photon back down. And because this is also a reflective surface, it will bounce it back up. And so what you're going to see basically now is a photon beam bouncing up and down between the two panels that reflect it on either side. And this then can be used as a time measuring instrument, which is called a light clock. The consistency of the bouncing photon can be used to measure 1 second for every cycle. So imagine that with each time that the photon touches top to bottom, 1 second has passed, right? 1, 2, 3, 4. So it's going to continue perpetually to achieve this reflection of the photon and measure light that way. Okay, now I want you to say, imagine that we have two of these light clocks that were of identical construction. So here's the top one and here's the bottom one. They're perfectly synchronized and they're in unison. So as the one moves up and down, so does the other. And they're like twin light clocks, okay? Identically organized, coming off the assembly line at the same time and keeping time exactly the same way. Now suppose we have an observer here. Here's an observer. Let's say that this observer and this light clock stand motionless, so they don't move. They stay in place. But the top light clock, we're going to accelerate to the right very, very fast, maybe even approaching the speed of light. We take this light clock above and accelerate it in this direction to the right. Now, the bottom light clock, the one that is standing still. When it's standing still, what's the angle of approach that the photon appears to take for this observer? It's a straight up 90-degree vertical line, like this. Because since that light clock is standing still, there's no occasion for a diagonal line to form since it's in place. But take this light clock that has now been accelerated while this man stands still and watches it. What do you think will be the angle of approach that this photon appears to take to the motionless observer? Will it remain a vertical line or will it not? What shape do you believe or angle will be achieved by this photon from the vantage point of our motionless observer as it speeds off to the right? What do you think? I'm asking you, what will be the angle of approach of the photon? Well, a horizontal line, no, Caesar, because that would mean that it's at such a velocity, like the speed of light, that it never even touches the top, right? Instead, it's not going to be quite a horizontal, but that's close. What would it look like? Because keep in mind, unless it's moving at the absolute speed of light, it's still going to bounce between the top and bottom. So what do you think will be the angle then? If not a horizontal, if not a vertical, it's going to instead look like a what? Just imagine yourself watching it yourself, and it starts accelerating. You're standing put. What do you think would be the trajectory of the moving photon viewed by the motionless observer as it bounces in between the top and bottom plates? It's not a right angle either, because a right angle is like a, I mean, are you talking about this? Like this? Like a right angle? No, because then there's no gradual anything. It's a diagonal, good. It's a diagonal because it's still gradually approaching the top and bottom, but to account for the speed, it appears to be a stretched out wave. Okay, so given its speed, it doesn't go in a straight vertical relative to this observer. It appears to be now stretched in a diagonal path. And the faster it is going, the more stretched out and gradual that diagonal will appear to be. Okay, this is completely understood and proven in other areas of science as well. Consider the Doppler effect when it concerns audio waves, sound waves. So if you know anything about this Doppler effect, then you'd be familiar with this explanation. Say that you're standing still and a car drives past you honking its horn. Okay? Now, you are standing still, but it's moving relative to you. As the car with the horn approaches and as it drives off, you're going to hear the pitch of the horn shift. As it's getting closer to you, it takes on a higher pitched frequency. And as it drives away from you, it takes on a lower pitched frequency. So this is like the experience of the observer as the car passes. As it's approaching, and then as it goes away, if that was a horn, you know, imagine. I'm not the best at impersonating a horn, but you hear that change in the modulation of the pitch. If you're in the car honking the horn, you just hear, you don't hear that variability. Now, what is the cause of the difference for the motionless observer while the car passes? As the car approaches them in its state of velocity, the sound waves between the car and the individual's ear get compressed, and that creates a higher spiked trough and amplitude of the sound wave, resulting in a higher pitched tone. As the car drives off away from you, the distance opened between it and your ear generates a more gradual amplitude and trough of the same sound waves, which generates that lower pitch. The reason that the person driving in the car doesn't hear this modulation is because there's not the same occasion for variability as the object in motion changes its orientation relative to the hearer. So that's how it works with sound waves. Photons behave somewhat as a particle and a wave. The wave-like properties of photons give rise to this similarity with the Doppler effect. The light clock that has now been accelerated at a high rate of motion is observed to be taking a more gradual pathway along its trajectory from top to bottom of each light clock cycle, okay? Now, the one that's still remaining at rest with our motionless observer appears to him to still be going just straight up and down in a vertical path. Question then. So say we took this top one, which we accelerated very quickly, maybe even approaching the speed of light, and we allowed it to orbit the Earth many times at that velocity. Finally, we return it back to its initial point and return it to a state of motionlessness and rest along with its twin clock. Now that this one has completed that high-speed journey and has returned to sit side by side with its counterpart, which of the two clocks would have recorded more seconds elapsed? The one that's been moving or the one that has stood still? One of them has now recorded more seconds than the other one, given the fact that one had been accelerated and one was not. Which of the two has elapsed more cycles of the photon touching top and bottom relative to the other? The still one, the one on the bottom, has ticked more seconds. And why is that the case? It's because it has a shorter distance to travel to achieve one cycle. It merely has to go straight up and down in a vertical direction of travel. But this photon, from the vantage point of the motionless observer, appears to traverse an arc, an angled diagonal. Thus, there's more space required for this to achieve one cycle than its motionless twin. So here's such a strange outcome then. When the two clocks have been joined back together and reunited, now they're both at rest again after this one's completed its high-speed journey. This one has more seconds recorded than its twin does. And that's just so strange because what it means is that they've aged at different rates. The basic rule then is that the fast-moving clock has passed through time slower than its stationary counterpart has. If there was another observer traveling with the velocity of the moving clock, then because they're traveling with it, they only see it going up and down as a straight vertical, while motionless observers outside of that moving reference frame see the diagonal pathway. So a motionless observer traveling with the clock would also pass through time slower. Observer in motion traveling with the clock would actually observe time passing slower relative to a counterpart that stayed at rest with the other clock. This gives rise to a very strange paradox of physics, which has been called the twins paradox. Okay, so imagine then that we took two identical twins. And as you guys know, identical twins are roughly the same age, born at the same time, basically, so same age. But take one of those two twins, place them The time differences between galaxies? Well, Brian, I mean, it would depend on the velocity of the objects moving in the different galaxies. If in one galaxy the object is moving much, much faster than it is in others, then they would not have a common rate of time passage, no. But let me go back to my quick example here involving this last point. It is kind of like in the movie Interstellar, yes. Some of those climactic scenes involve that exact theoretical result. So yeah, you've got one twin. They're accelerating far away from the planet Earth, moving very fast. Their identical twin stays at Earth, staying at rest. When the fast-moving twin returns from their interstellar travel, they'll come back and they will find that their identical twin is what? Older or younger than them? What do you think? The fast-traveling traveler reunites, family reunion with their twin, and the twin remaining back at home is now way older. The twin remaining back at home is the equivalent of the light clock that has stayed motionless while the other one has zoomed through space quickly. It has been able to record more seconds because of the shorter angle at which the photon has to bounce. So that's so strange, isn't it? Think about that. If you're born and you have an identical twin, you're used to the idea that you guys are going through life at the same age. But how about if one of you just accelerated your body very quickly, and depending on how fast and for how long you were traveling at that rate, you're now passing through time at a slower rate than your twin. So you would actually return to a planet, Earth, with your identical twin being, I don't know, 5, 10, 20 years older than you, depending on how long you traveled and how fast. How strange is that? You would think that time and how fast it passes can never differ from person to person, that there's a universal clock that we all pass through at the same rate. But this theory of relativity does show us that this is not correct at all, that the amount of time that elapsed for a given observer will differ from others if their rate of velocity is different relative to one another. But I have another couple questions. This twins paradox, since it is true that time dilation is real according to one state of velocity relative to others, how come we don't observe or notice the effect of this in everyday life? How come, for example, people that travel a lot on jets, flying around a lot, jet setters, or people that just drive really fast on the freeway, or runners that are constantly moving quickly, how come we don't see these people having less time passed than others who don't travel as much as them or who don't move as fast as them? If this is a correct result, then how come we don't ever notice it by means of seeing people moving more quickly, aging slower than people who are moving less quickly? How come you don't think we notice the effect then if it's true? There's a reason for that, and I just want to see if you have a thought about what that reason might be. If time dilation does happen when some objects move faster than others and causes them to therefore pass through time slower than those others, then how come this is not noticed or observed in human life when some people, let's say, travel more than others or move faster than other people overall? How come we don't notice it then if it's true? What do you think is the reason we don't? Good, exactly, William. It's because the variability in our different speeds is not significant enough to make this affect anything more than infinitesimal on the terrestrial earthbound surface that we live on. Exactly, Emily. So yes, in fact, it's true, though, when you are flying in the plane going at like 600 miles per hour and people are staying down on the surface of the planet standing still, you actually are moving through time at an infinitesimally slower speed than they are. But since that is a degree of variability of like 600 miles per hour, it's not enough to make the effect anything that would be on a macroscopically observable level. If we could, though, achieve variable speeds that were highly divergent, like some people moving close to the speed of light and other people staying still, then there would be major time dilation effects that would occur, and it would become impossible for us to synchronize our watches and stuff, because some people moving closer to the speed of light would have clocks passing through time slower than people that were not moving at that same rate. So for good or ill, we're kind of bounded on the Earth, and even the top speeds we can ever achieve don't make it possible for these effects to be anything that's really seen in a broad sense. To achieve speeds that fast for a human body, by the way, the prospects are not too good. It'd probably rip you apart with the G-forces if you could ever even go somewhere close to that speed. But what we can do, and what we have done, is prove this through the use of elementary particles in particle accelerators. With these particle accelerators that we have built, like in Switzerland and places, we can, in fact, accelerate tiny little electrons and photons and stuff close to the speed of light. And when we do that, the exact predictions of the theory are observed, that the half-life of those particles extends as compared to the half-life of particles that are not accelerated at the same speeds. So there's proof of this empirically. Also, there's empirical proof of another kind. During Einstein's own life, they wanted to test this hypothesis, so they took two clocks, which were like nanosecond clocks that could record time way down to like 100 decimal points after zero. And they were perfectly synchronized. They placed one of them in a jet that would circle the Earth going at Mach speeds, so several times the speed of sound at least. And then another one staying on the surface of the Earth. When they reunited the two clocks, the degree of divergence between the recorded time was exactly what was predicted by the mathematical formulas of the theory. So there actually is proof that this is real. And once again, it's so trippy and strange, because imagine you could like step into like a centrifuge that would spin you around close to the speed of light for some duration of time. And then you emerge from it and the world around you is like 20 years older, but you got in there and you spent 5 minutes or 10 minutes relative to your own clock on your wristwatch. So this is strange stuff. It just shows you that time and space are linked together, and how fast or slow objects move through space relative to others does in fact change and distort and dilate the nature of time's passage for that person. Okay, so interesting and weird stuff to finish off the Einstein. I just wanted to add those notes about twins paradox and time dilation. And this is all, this is all scientific consensus stuff. This is not like just pure metaphysical speculation. It's all backed by empirical studies that have been well confirmed over and over again and replicated. So, interesting stuff. But I want to go on, because we have a few more pieces on this matter before we're done this week with the subject of time. So the next author on this is American philosopher Theodore Sider, but he's known as Ted Sider to a lot of people in the field. So Ted Sider. So this is a current day philosopher born in 1967. And the paper that we're looking at from him, it comes from a book he wrote in 2005, but they've retitled it in our text and just called it Time. So Theodore or Ted Sider, Time, from 2005. His goal in this paper is to sort of just lay out the fundamental puzzles and paradoxes that arise when you start trying to think about the nature of time beneath the surface depth. And he says this to begin. He says, talking about time and investigating it is difficult for us people because it's something that we usually just take for granted and we don't think has to be really investigated further. It's sort of like the air that we breathe. We just breathe the air. We don't really think much about inhalation and exhalation. It's just an autonomic process of the nervous system. But if you stop and think about it, it starts to almost seem like a labored effort. Like, wow, I have to keep drawing in these breaths all the time. That's a little bit of work. Another metaphor, fish, they swim in the ocean. They're surrounded by water. Literally, they're immersed in it. But it's not like probably a thing that a fish would do, even if it had the intelligence, to step back and question, well, what is this water, though, that I'm always constantly surrounded in? It just lives with the water and it deals with it, but it doesn't ask a question about it because it's something that's a given. Time is kind of like that for us. We live our lives according to the clock. We are always aware of the passage of time and all of that. But we don't usually step back and ask questions like, well, what is this thing that we're living with, which is called time, and what's the deeper analysis of it? Because it's taken for granted. But Ted Sider says we shouldn't take it for granted, though. We should actually investigate it in depth. Because the thing is, when you start to look at it beneath the surface, you see that it's very puzzling, confusing, even paradoxical, the common ordinary sense of time. So what is so weird and puzzling about it? He says one thing that's strange about it, he says time is puzzling because people say that time moves, okay? People say that time moves, but what does that mean? What does it mean? So first big problem that he thinks we need to put on the table and ask a question about is, what are we saying when we say time moves? That's a common expression, and people use it all the time. But what are we saying? Like, what's the explanation of what that means? And how many common everyday phrases are there that give some indication that we think of time as moving? Sometimes we say time flies. You've heard that phrase, time flies, but flying is a metaphor for motion. So it's something in a state of movement. Time passes. People say that. Passing something is to move beyond it. Time is flowing, people say. You know, time's flowing. I'm caught up in the flow of time as though it's like a river and I'm just moving with that current. They say time marches on, right? Time stood still for a moment, you know? So people talk about time as a thing that is in a state of constant motion. These everyday cliche phrases give sense of that. But the question now is, what are we saying and how does that get explained? The flow, the motion of time. The reason that he says it's very difficult to explain the concept of time moving is because movement itself is defined in terms of time. Okay, so let me erase a little bit here. Explaining how time moves appears puzzling because the concept of movement or motion depends on time. Okay? So let me go over this point that when you explain the idea of motion, even through space, you have to make mention of the concept of time. So, like, for example, now, my hand, I'm making it into like a little walking stick figure kind of thing. Suppose I'm going to have my hand move from here towards, like, I don't know, the corner of that textbook that's on the other part of the table. So here, let's observe movement. Starting here at point A, over here is point B. Okay, now what happened right there? The hand moved. For the hand to move, it had to be at different places at what? How would you complete that sentence? So for my hand to just move, like even from this side of the board to that side of the board, it has to be at different places in space at what? For anything to move, if you just think about it for a half second. For something to achieve movement, it has to be at different places at different times. Exactly, William. But there's the problem. If we say that time moves, and movement means things are at different places at different times, then for time to move, time would have to be at different places at different times. But that now is using the concept to define itself. Time is ordinarily used in an effort to explain what motion is through space. But if we now claim that time is itself a thing that's somehow moving, then we would have to appeal to some secondary notion of time to organize the movement of the first order kind of time. So if time moves, then it's in different places at different times. But we are already talking about time, so how can we appeal to the concept in order to explain it? That's circular. To give a diagram here, which is also shown on page 458 of the book. This diagram is supposed to give an indication of how we ordinarily define motion. So here's the figure. There's 4 horizontal lines. Okay, and I'm going to put 4 time coordinates to the left on this x-axis. So T1, T2, T3, and T subscript 4. Now, underneath the 4 horizontal lines, we're going to write the names of 4 places that a train is going to travel as it goes along a given journey. So starting in Boston, then New York, then Philadelphia, and then finally Washington, D.C. So the same 4 city names are placed in that sequence under each of the lines. All right, now, say a train is going to make a journey starting in Boston, departing from Boston, and final destination Washington, and it travels through the different cities as it makes that path. So train begins here, Boston. That's the initial time. Later on, subsequent second later time, it's in New York. At a third time further, it's in Philadelphia. And then finally, at a fourth time, it's in Washington. This graph sort of graphs the movement of a train in space as it goes from point A, Boston, ultimately to point B, Washington. But look at how we had to organize this graph. To indicate that the thing has moved, we had to say that it's in different places at different times. Now, if this was a different graph, and what we had was the train like this, Boston, 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 was that a moving train? If we drew that graph that shows that at time 1, 2, 3, and 4, it's just Boston the whole time? No, that would have been a train that never departed the station. In other words, that would be a train that is in the same place at all different times. In other words, not moving. So for something to achieve movement, it has to be in different places at different times. If it remains in one place for all time, it remains at rest and doesn't move. The thing then is that obviously we're using time in a definition of movement. So if time is something that moves itself, then we would have to use the concept to explain itself. We would have to say that time moves by being in different places at different times. And therefore, we're using an undefined concept in order to explain itself, and we're going in a circle. Well, maybe there's a different way to explain this, he says. So attempt number 2. Not just to say that it moves by being in different places at different times, but maybe what we mean when we say that time moves is that the present moment is constantly moving. Maybe this gives the correct expression of the idea that time moves. But he says ultimately that's not going to work either, but let's just try the suggestion out. So a new graph. So here we have our 4 horizontal lines. And these 4 coordinates here to the left. So that's a lowercase t with a subscript to stand for time. So we got T1, 2, 3, and 4. Now, underneath the 4 horizontal lines, I'm going to draw 4 different times according to the clock during a given day. Starting with noon, 12 noon. Later on, 3 p.m., 6 p.m., and then 9 p.m. And that gets reproduced on each of the horizontal lines underneath. You'll see the same graph here in page 459 of the textbook. Okay, so second attempt to explain how time moves, so to speak. Maybe it's because the present moment is always moving. So for example, in a given day, at one point in time, 12 noon is present, right? But it doesn't stay 12 noon the whole day, right? That's present for a while. But then later on, subsequent to that, 3 p.m. is the present moment. And then even beyond that, 6 p.m. is present at a third later time in the day. And then finally later on, getting closer to the evening when you're going to maybe start taking to bed, 9 p.m. is the present moment. So does this give an adequate explanation of time moving? At first, it sort of looks like it. And let's just try to make this relatable to you right now. Okay? So I'm looking at my watch. It's 10:40 a.m., April 13th, 2020. Okay? That's the present moment right now. Like, this is current. This is what's happening right now. This is not in the future nor the past. This is live. This is present. But it has not always been the present moment, right? Earlier today, this morning, when you woke up, I don't know, let's imagine you woke up this morning at 8 a.m. Back then, that was the present moment, and this was the future. But right now, when you woke up is in the past, and this is happening live. And a later on time today is in your future right now. But when that time point happens, then that'll be the present moment. So right now, like noon, 12 noon today is future. But at a later on moment during our day, that'll be the present moment. And then this will be the past. What's happening right now, of course, will recede into the past. So you could argue that the present moment keeps changing its position around. And now that's what we maybe mean when we say the time is moving. The present moment just shifts its position according to the clock as time passes. But there's still a problem, as the author is going to point out, okay? And here's the real problem. To draw this graph, we had to place these 4 coordinates on the left in order to show that time, the present moment, it's not staying in one place, but it's moving according to the different times along the day. But notice that these 4 coordinates on the axis here are time coordinates, T1, T2, T3, and T4. So now we have just another big question. How are these time-like coordinates going to be assigned that linear ordering 1 through 4? In order for them to have a sequence that they occur within, it would appear that they need to be placed in a tertiary sort of graph, according to which they're organized in a higher order sort of time. But now we're leading towards an infinite regress. Time, the present moment, moves with reference to some secondary notion of time, and this secondary notion of time has to be organized with regard to an even broader scope of a third order sort of time. So we keep having to use the notion of time to define and explain its own movement. Therefore, Sider says we have to completely go in a different direction. He proposes a different strategy then. He says, better to just abandon this entire effort of trying to express what it means for time to move. A way of getting away from that whole idea is to simply embrace the work of Einstein and the space-time theory. According to the space-time theory, time does not move. It just holds all the moments of space-time together in one integrated framework, and all the moments are equally real, inclusive of past, present, and future. On that conception, there's no puzzle to be explained because it simply is now denied that time moves. Time doesn't pass or unfold. It just contains all the events in space-time, kind of like a big, sometimes it's called block universe theory. So every moment of, for example, your entire existence and the entire existence of the planet Earth and the universe is fully laid out and already objectively real. The order of your experience then would appear to be the illusion of there being a past, present, and future occurring in a specified ordering. But on the space-time theory of Einstein, to accommodate the results of the simultaneity of relativity of simultaneity, we actually will deny that there is an objective sequence of events, because again, if one event is in the relative future of a given observer, but it's in the relative past of a different observer, then there's no fact at all about which one of those events occurs first, and they have to be granted equal reality. So in this way, we abandon the effort to explain that time moves, but now we have to hold to the Einstein space-time theory, which does have its own kind of weird puzzling elements to its own. For example, the notion that all the space-time events are equally real would seem to contradict views that we have about the openness of the future and our free will. You sitting there right now believe that whatever will happen to you next is something that is undefined because the future is yet to exist. On the space-time theory, all events inclusive of the full future are already just as real as the present and past. So if that is the case, then you're actually not capable of doing anything other than what you actually do in life. And that would seem to contradict the widespread belief that most have, that your future is completely under your control, and that by making free will decisions, you will determine how the course of events plays out. On the space-time theory of Einstein, this is given up, but one benefit of doing so is that we're now free of the difficulty of explaining how it is that time moves. So let me read that from his work. He says, time's motion has us all tangled up in knots. Maybe the problem was with that idea itself. According to some philosophers and scientists, our ordinary conception of time as a flowing river is hopelessly confused and must be replaced with the space-time theory, according to which time is like space. Now we're going to go further next time into the last few details of Ted Sider's work, and we're going to talk about how he expands on what space-time theory is and how to replace our everyday conception of time moving and flowing with this scientific perspective of space-time theory that denies that there is such a thing as the passage or flow of time. But what he ultimately will say here is the space-time theory avoids the paradoxes of time's flow, and that counts in its favor. Let's see a little bit more here. In contrast to the ordinary conception of moving or flowing time, The space-time theory says that reality consists of a single unified space-time, which contains all of the past, present, and future. Time is just one of the dimensions of space-time. Time does not flow. Time is like space. So on the space-time theory, you would actually reconceive of your ideas of time as being much more similar to space. It's something that merely contains all the events jointly together with space. Just like the universe, we don't say flows or passes, but it's just a container holding all the things. Time integrated with space is like the container which withholds all events of the full past, present, and future. Now, I can't really, I think, give more expansion on this with this brief few moments left in class time. Caesar question, could you say that you do have free will, but that all the choices you will make in your life have already been made? Interesting question, Caesar, and to be honest with you, I have a view about that. I've published, I presented some papers at some conferences on this exact question. What is one to do if Einstein's space-time theory is true? Is one to assume, therefore, that free will does not exist? Or is it possible to articulate a conception of free will that's compatible with not being capable of doing otherwise? I actually do think that free will can be understood under the space-time conception, but it's a different notion of free will than the ordinary one that most people have. When you think of free will, you usually think of it in a very robust sense, meaning that you're free to do otherwise and counterfactual possibilities are open to you. On the notion of free will that I defend in this other paper, I say that if Einstein's correct, then you cannot literally do otherwise than what you actually do. So free will does not consist in that, but rather I think it has to do with being able to be aware of the reasons that you're acting. So knowledge of why you are doing something, comprehension of the reasons that you are doing it, is what would count you as a free agent. A leaf blowing in the wind doesn't have consciousness, and it doesn't have any sense of why am I floating towards the left or to the right. But you and I have consciousness, and therefore when we act, even if our actions are dictated by the larger circumstances of space-time and physics, we are aware of the reasons why we're doing it. So I think comprehension and knowledge of your actions' reasons gives you a semblance of free will. But it's not the same thing as being able to do absolutely anything, because according to the space-time theory, your actions are already fully governed by the timeline of events that exists. So that's a deep question. Some people would deny that this is a fair-minded analysis of free will because some people think you have to be absolutely able to do otherwise in order to be free. Like doing otherwise, for example, you're watching this lecture right now, and that's fact. But could you have been free to not watch the lecture today? Now, your ordinary response probably is, of course. I could have slept through it. I could have decided I didn't want to watch it. And if I did that, then I wouldn't be watching it right now. But those counterfactual possibilities of you deciding otherwise did not happen. So it's kind of, in a way, just purely based on the idea of you being able to do something else. But what you actually do in life is only the actual behavior. The counterfactual behaviors, the behaviors you could have done contrary to fact, by definition, don't happen. So there's only one stream of actual behaviors you ever elicit. And you'll never be able to prove your ability to do something otherwise because you never do anything otherwise than what you actually do. So it's kind of strange, isn't it? Are you really free? We feel free. Like, for example, if I'm free, then I can make a choice right now whether or not to pick up this eraser that's on the table. So look, I'm free. I'm going to do it. No, I'm not. Wait, yes, I am. Okay, now look. Did I do something that wasn't supposed to happen there? Like the action of picking up the marker was something completely within my control. I had the choice to do it or not do it. There's a larger story you can tell about the physical circumstances I'm in, which would have it that neurologically, physiologically, and otherwise physically, it was determined that I would have picked it up as I in fact did. And the illusion in my mind of having the matrix of choices is just something that's mental but not actually objectively real. Well, it's all very interesting. And if you guys ever study at a higher level of physics or any of these questions in science, you'll get a different taste, but they're also of interest to philosophers. So are we able to perceive space-time? Yes, just look around you right now. There's a little part of it. You can only perceive maybe some of it at a given time because you're a finite being. If you're a god, maybe you could perceive all of it at once. But you can perceive the limited amount of space-time which you have access to. And maybe, with greater tools of observation in the future, we'll have even greater access to observe more and more. Certainly our ancestors without the same telescopes and so on didn't have the same kind of insight that we do, but we're living in an interesting time, I guess. So we have more to say, but we're running short on time, haha. So let's be back on Wednesday. I'll complete the last notes on this Ted Sider, and I just want you to read the work of David Lewis. We have 2 lectures this week that would have been given for a film, but I've just decided to slow down and give us more time to discuss the topics. So this week it's finishing Sider and reading David Lewis. Make sure you do that, and we'll be ready to go Wednesday. Other than that, have a great one, everybody. Stay safe, healthy, and take care. I'll see you really soon, okay? See you soon.